Hey guys, this is Mr. Maestas again, and we are going to look at some mixed problems. How do we determine what test to use? We've gone over all these different convergence and divergence tests, and at some point, especially if you're in Calculus BC, you take that AP exam, you're going to need to figure out which one to use on which type of problem. So what I thought I'd do here is provide you with some tips on deciding and kind of differentiating, how to decide which one you're going to use for which problem. So here's what you're going to do. Think about 4 real basic questions here. And I say basic questions, and you're like, these aren't basic questions, Mr. Maestas. They're not basic questions. They're hard questions, but I'm going to think about them anyway because you told me to. So here are the questions you need to think of. First, does the nth term approach 0? Now, if it does, then we don't know. We're going to have to use a different test. But if it doesn't, if the nth term does not equal 0, and we can see that right away, then we know that the series is going to diverge by the nth term test. So you always try that nth term test first. Then you ask yourself, is a series a special type of series? Is it geometric? Or is it a p-series? Or does it alternate? Maybe I can use the alternating series test. If it's one of those special types of series, then use one of those 3 tests: geometric, p-series, or alternating series. If you can't, then let's think of another one. Let's think, okay, can I integrate this bad boy? Is it something that I think I can integrate easily, or I can see in it somewhere where it has some integration I can deal with? If it does, then I can use the integral test. Or does it have factorials and exponentials that I can easily get rid of, like we did in the ratio test just in the last video? If we could do that, then we're going to use those ratio tests or the integral test. Lastly, if we could see that it has something that we may be able to compare it to, maybe a larger or a smaller series that we know we can use a direct comparison test, or something with messy algebraic stuff that we know we can use the limit comparison test, because once we use that ratio that we get rid of with the limit and we compare it to, we can simplify things out. We would use the limit comparison test. So I know that seems like a lot of stuff to kind of think through, but that's the process. I think that if you think through those in that process, you'll be able to come up with the right test to use. So just in review here, okay, all of a sudden my thing's not working. In review here are the convergence tests, the convergence and divergence tests that we use in Calc BC or in Calculus 2. So you could take a screenshot of this or whatever, and I'm sure my head might be in the way, so I'll shrink this down for you. And if you're in my class, you have this with you on your book. Okay, so let's take a look. We'll use this. We'll take a look at some examples here and try to differentiate. I guess say it again. Try to figure out what test we're going to use for which one. All right, so let's take a look at these examples here. So we'll start with here example number 5, the series n equals 1 to infinity of n minus 1 over 2n plus 1. Now notice here that the limit, the bottom is getting bigger faster than the top is. However, if I took the limit as n approaches infinity, I have the exact same power on the top as the bottom. So this is going to be 1/2, right? Horizontal asymptote, right? 1/2. So since it equals 1/2, this diverges by the nth term test. That one's pretty quick and easy. Let's see number 6. So we've got this n squared e to the negative n cubed. If I took that and brought it down to the bottom, I'd have e to the n cubed in the denominator, and that would grow pretty fast. So that limit's going to be equal to 0. So I wouldn't want to use the nth term test. So can I differentiate that? Well, look at this. The derivative of negative n cubed is negative 3n squared, and I already have the n squared there, so it looks like I have the the beginnings of a reverse chain rule. So it looks like I'm going to use the integral test. So I'm going to go and try the integral test. Limit as b approaches infinity of the integral from 1 to b x squared e to the negative x cubed dx. And I have a hook. So I'm going to put a -3 in here and a -1/3 out here so that this is my hook for the reverse chain rule. And if those of you that are going, what is he doing? I'm doing the reverse chain rule. You can go back and take a look at my video on reverse chain rule. So then this is going to be -1/3 e to the negative x cubed, because the antiderivative of e to the anything is just e to the anything evaluated from 1 to b. So I'm going to have the limit as b approaches infinity of -1/3 e to the negative b cubed plus 1/3 e to the -1. So this I could rewrite as -1/3 e to the b cubed, and this is 1/3 e. Now when I take the limit as b approaches infinity, this is going to go to 0, and I'm going to be left with 1/3 e. So since this equals to a value here, L, we know that this series converges by the integral test. All right, so we've decided that was the integral test. Let's take a look at another one. This time I'll go with blue just because it's something different. So e/3 to the n. Anytime we have a fraction or something raised to the n power, we're probably going to think this is geometric. So this is a geometric series where r is equal to e/3. E is about 2.7, so 2.7/3 is in fact less than 1, so we're good to go there. So we're going to say the series converges by geometric series test. All right, that was pretty quick. If we compare this to the harmonic series, compare to 1/n, if we try to do a direct comparison test, because really none of the other things really work out. So we see here we can try to compare it to 1/n. The problem is 1/4n plus 5 is going to always be less than 1/n. But we can use the limit comparison test, and that might work out. So let's go and use a limit comparison test. And we know that this diverges. So we're going to go and take the limit as n approaches infinity of 1/4n plus 5 times n, right? n/1. We're using the limit comparison test. And that's going to give us 1/4. So since this is finite and positive, the series this one diverges by the limit comparison test. Okay, because since this diverges, this is going to diverge because we got a finite number. All right, let's take a look at the next one. Oh, what do we know about this one? This one alternates. So I know that it alternates. I think the first thing I'm going to try is the alternating series test. Limit as n approaches infinity of 3/n squared is going to give me 0. 3/n squared always decreases. So since this always decreases and my limit was equal to 0, the series converges. By the alternating series test, all right? Okay, let's take a look at one last one here, and we're good to go. Wow, what's going on here? 1 times 2, 1 times 2 times 3, 1 times 2 times 3 times 4, 1 times 2 times 3 times 4 times 5. That looks like an n factorial over 10 to the n. All right, so I first should change it to sigma notation. So now that I have in sigma notation, I can see what's going on. I have a factorial and exponential. Boom, I know exactly what to use on that. We are going to use a ratio test. So I'm going to go and do my ratio. The limit as n approaches infinity of n plus 1 factorial over 10 to the n plus 1 times 10 to the n over n factorial. Boom, 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 boom. We get limit as n approaches infinity of n plus 1 over 10. That's equal to infinity and beyond. That diverges by the ratio test. All right? Boom. So there you go. That is a strategy for finding and choosing the right convergence or divergence test for your series problem. Boom.